So I'm going to talk a little bit about the potential energy and how that relates to excitation and de-excitation, and explaining why you have to get work or energy out from de-excitation and why you put energy in to cause excitation. So first, some basics, the equations that you should know. So potential energy is the charge moving in the field multiplied by its potential at the point it's at. And in terms of radial fields, the potential energy is the charge that creates the field multiplied by the charge travelling in the field divided by 4 times pi times the permittivity of free space times the distance between those charges. Other key points. To calculate the work done or work out, you need to know what the change in the potential energy is. So you need to know the potential energy at 2 points, and it's the difference between those that gives you amount of work. And if your work is positive, that means you're having to put energy in. And if your work is negative, that means you can get work out of the system, so you get energy out of the system. So that would be, in the case of de-excitation, emitting a photon. And we're going to prove that in the next slide. So what we've got here shown in the diagram is an electron de-exciting from the second level to the first level. So if you remember our quantum numbers, say it's going from n equals 2 to n equals 1. So what we've got in the middle here is a nucleus with Z numbers of protons. Z is a proton number, so I'm not being too specific here. So you've got a nucleus filled with Z protons, and you've got an electron here in n equals 2, and it's de-exciting to n equals 1. And what I'm saying, just for the purpose of this example, is that n equals 2 is twice the distance from the nucleus that n equals 1 is. And again, for this example, I'm just assuming there's a 1 electron. I'm not thinking about the shielding provided lots of electrons, that sort of thing. That would make it way too complicated. Nice, simple example, 1 electron, a nucleus with an undefined number of protons, de-exciting from n equals 2 to n equals 1. So we want to work out the change in energy. Because at this point, I'm not even going to assume that we're going to get energy out in the form of a photon. We're going to prove it in terms of the equations, what happens, but bearing in mind what I said in the previous slide about whether what work being negative means and what work being positive means. So if we want to calculate the work done, we need to know what the change in the potential energy is. So it's going to be the final potential energy minus the initial. So it's going to be P2 minus EP1. I'll just show you, so it starts off at state 1 and it's going to state 2 here. So we need to be able to calculate what those energies are. So let's do that. EP2 first of all. It's going to be the number of protons, so the charge of your protons, making sure you multiply by 1.6 times 10 to the minus 19. We've got the charge of moving in your field, so that's just your electron. And you've got R, so in the second state it's at distance R. And in the first state, it's going to have ZEE again. We're going to have this 4 pi E0, but it's going to be 2R. And remember that to do work you need the change in potential energy. So let's do that. Let's put those two at the top out of the way. So the work is going to be your final state, so at 2, the state at 1. So let's factorize this. And then if we do that, so it's sort of like 1 over r minus half of r. So that's just going to end up being ZEE 4 pi E0 1 over 2R. So things to note about this. We said that if work done is negative, then that's going to be getting energy out, which is what we'd expect as a photon is emitted. So let's have a look at whether this is going to be negative or not. So first things to note, if we look at this bottom line here, these are all constants and they're all positive, so that's not a problem. Those are all going to be positive, they're not going to change anything. R is a distance, so that's always going to be positive, so that's not going to change to tell you whether it's positive or negative. This here is your proton number multiplied by the 1.6 times 10 to the minus 19. It's going to be a positive number, but this one, the charge of an electron, remember, is minus 1.6 times 10 to the minus 19. So this is going to mean that whatever radii you use to calculate this, this is going to end up being a negative number always if it's going from a further away to closer in, which means you're always going to get energy out when you de-excite from further away to closer in, which is why you always get a photon emitted. If we think about it the other way around, if you were doing excitation, these two numbers here would be the other way around, which means over here you would have ended up with minus 1 over 2R there, and minus there and the minus for electron would have cancelled each other out and left you with a plus, so you'd have been left with a positive work. So to go to excite, to move the electron further away, you have to put energy in, which correlates with what you would have learned about at AS.